Alright, so now that we have a pretty good understanding of how to reverse a linked list and how to detect cycles, let's now go into actually implementing the code. And turns out that once you understand how basically the structures work and how the pointers basically change within these linked lists and all that stuff, what you have to return, turns out that the actual code is not that bad. So I'll show you, let's just go straight into reverse. So remember, we're building reverse from the back of the reverse list to the front, and we're basically going through our original linked list from the left to right. So what's the last element of the reverse list? It's gotta be basically the empty linked list. So I'm gonna first start by making reverse link.empty. And the reason I'm doing this is, let's also think about the simplest possible case. If my linked list is empty, my reversed linked list is empty as well. So this is a pretty intuitive initial starting point. And so what we're going to do is, while it's the case that my link is not link.empty, I'm going to update my reversed by taking the first element and putting that at the back. So my reverse is now going to be basically calling link on link.first and whatever I have reversed so far. And then I, of course, have to advance my way to the linked list. Oops. Link is equal to link.rest. And then at the end, I return my reverse. So then let's go into hash cycle now. So hash cycle is a little more tricky because we have to basically keep track of 2 pointers. But one case to think of is, again, whenever you're working with linked lists, the first 2 cases that you should automatically pop into your head. Hey, what if my linked list has no elements in it? It's an empty linked list. And also, what if my linked list has only 1 element? Because those are generally 2 special cases. And in this case, we have to think of that because we know our fast pointer is going to be going 2 at a time. So if it's only a 1 element linked list, it's not going to work. So that's the key idea there. So, and also, if it's only a 1 element linked list, we know it doesn't have a cycle. And if it's an empty linked list, we know it doesn't have a cycle. So we can take that logic directly, and we can say, hey, if the link is link.empty, or basically it's a 1 element linked list. What does it mean to be a 1 element linked list? Well, that just means that the link.rest is link.empty. Then we can return false immediately. It doesn't have a cycle. There's no way an empty linked list or a 1 element linked list is going to have a cycle. And now what we can do is we can assign our slow and fast pointers. So slow starts at the beginning and fast starts at the beginning. And then while it's the case, so when do we know that we can stop, basically? Well, if the fast pointer reaches the end, then we know we don't have a cycle. But we want to keep on updating our fast and slow pointers until we know that the fast has reached the end. Or if it hasn't reached the end, we know that the slow and fast pointer is going to meet. So basically, our while loop is going to make sure that the fast is not at the end. So what does it mean for the fast to be at the end? Well, basically the fast has reached. So while the fast is not the link.empty linked list, then we have to do something. But also notice that we're incrementing fast, or not incrementing, we're going through the fast pointer 2 at a time. So we also have to make sure that we don't get any weird errors by having our fast pointer, fast.rest pointer being the empty linked list. So, and we have to make sure that the fast is not, we have to make sure that fast.rest is not link.empty. And the reason we have to do this is because if we want to advance fast 2 at a time, we have to do the following. So do fast.rest. And we cannot do this if either fast.rest is link.empty or fast is link.empty. So that's the key idea there. And then of course, our slow pointer is pretty easy. We just slowly advance our way through the list. And then, now once we've advanced our pointers, the first thing we have to check is, hey, do we have a cycle? And how do we know if we have a cycle? If the slow and fast pointers meet at some point. So if the slow is the fast pointer, then we return true. This is a cycle. And then, otherwise, if it breaks from this while loop, that means we've basically reached the end. So there's no way, the fast pointer has reached the end, so there's no way there could have been a cycle. So that's the logic here. So let's test these 2 functions. And they work. So again, this is something very hard to come up with if you initially just try to crank out the code. So make sure you take a step back sometimes and just see how would I basically design something like this, because it's really important to we did a lot of diagramming of the linked lists, how they change, and that's a very good method of programming, because you always want to think before you program. Because one thing you don't want to do is you don't want to just basically crank out one line of code and like a couple other lines of code and a lot of lines of code and then see everything fail at the end. That's going to be very frustrating. So this will prevent you from getting too frustrated, because you'll actually be thinking about how it works rather than just cranking out the code. Alright, so now that we've gone through some linked list methods, or functions I should say, with the hash cycle and reverse, let's now go into the infamous tree class. I know we all love this one. So we obviously have a handy isLeaf method, or I should stop calling them methods, they're functions, my bad. And we also have a new function we're going to define. So we're going to call this function contains. It's pretty straightforward. It's just going to be, hey, if the element that I want is in the tree, return true, and if it's not, return false. So that's going to be basically what this function is going to do. So the first thing is, as with any tree, we want to think of the simplest possible case. Well, in this case, it's actually not the fact that it could be a leaf. The simplest possible case is whether my initial entry is the element, because then I know for sure it contains it, right? So if my t.entry is equal to the element, then I know for sure that this contains the element. So pretty intuitive there. Now, what is another case? Well, if we think of a case that's true, it just makes sense that we should also think of a case where it's false. Well, so now that's the tricky part. So what in this example makes this false? Well, 4 is obviously not in the tree, but basically I went through all the branches and I couldn't find it. So how do I know I went to the end of a branch? Well, if it's a leaf. So now the key thing why I didn't define this first is because I have to first check if that entry is in the leaf is equal to the element. But if this ended up not being true, and it's a leaf, then I know that I'm basically done. This is false. Okay? Now, the last thing is of course the case where it's not a leaf and it's a more complicated tree. So what we can do is if we've gone through the root element and realized that it doesn't have the entry, the problem is basically the same, except now we just look at the subtrees. Does T1 contain, the subtrees of T1 contain 2? That basically will give you the same answer as whether the entire tree contains 2. So that's the key idea here. So how do we check if something is contained in a tree? Well, we have a function for that. So here we have another recursive definition. And so what this recursive definition is going to do is it's going to check if my element is contained in my subtrees for every subtree in my branches. Okay? Now, the key idea now is to think, hey, what does contains return? It returns either true or false. How do I know? So I'm going to get a list of true and false elements, basically. How do I know that something contains the element I want? Well, basically, the way I know that is I only need one of these elements to be true. So basically, true has to be in this list. So we can basically take that logic directly. Return whether true is in my list that I created. And this is a Boolean expression, so it's going to return true or false. So let's test this out. And it works. So that's our contains function right there. And so the key intuitive leap is to notice that you can basically cast the problem of whether the subtrees have an element. We basically only need to check if one of these return true. And if one of them return true, we know it contains one of the subtrees contains the element, and that's all we need to know. It's not asking whether there's multiple instances of the element. We just want to see if it contains one of them. So that's the idea there.